Hi everyone, I'm Yeji Kim from the Catalyst for Eco-Friendly Energy Laboratory. I will start the presentation about my research field. The title is CO2 hydrogenation to hydrocarbon. Global warming caused by carbon dioxide in the atmosphere is getting more accelerating, and global average temperature steadily increasing. Therefore, the carbon capture, utilization, and storage, named as CCUS, is emerging as an important technology worldwide. CCUS is a technology that can capture and make effective use of the high concentration of CO2 emitted by industrial activities. In case of CCS, captured carbon dioxide can be stored on geometric or in the ocean. And in the case of CCU, CO2 can be converted into chemical feedstock like carbonate, urea, or fuel such as gasoline, formic acid, and methanol. Recently, alternative energy such as hydrogen energy is being developed, but there are some problems such as in infrastructure and technical problems. Therefore, it is predicted conventional fuel will be steadily needed, as shown in the right figure. Therefore, research for converting carbon dioxide into fuel are being researched. Among them, CO2 hydrogenation is the one of effective methods to convert CO2 into various chemical variables. Therefore, I am researching the reaction of CO2 hydrogenation to hydrocarbon that can produce various fuels. This technology is a process that connects the existing two processes in two steps. First, there is the reverse water gas shift reaction named as RWGS that produces CO and water from CO2 hydrogenation. And the second, Fischer-Tropsch synthesis, which reacts a syngas that consists of carbon monoxide and hydrogen to produce hydrocarbons. These hydrocarbons are used for various fuels. C1 is the natural gas, C2 to 4 is petroleum gas, C5 to 11 is gasoline, C12 to 20 is diesel, and C21 plus is wax. The formation of large amounts of methane is undesirable, since it represents a loss of carbon that or otherwise could be directed toward liquid products. These two reactions can proceed simultaneously to produce hydrocarbons directly from carbon dioxide. Below is the mechanism on the cobalt-based catalyst. Although the mechanism has not yet been clearly identified, there are typically two pathways: the H-oxys pathway with formic acid as an intermediate in the cobalt oxide active site, and second one is direct pathway with metallic with CO as an intermediate on the metallic cobalt base. In general, FT has good carbon chain growth activity, but CO2 has relatively low activity due to its high thermal stability. So the FTS process has been commonly serialized as follows, but CO2 hydrogenation has not yet. So I prepared the previous research paper. In this reaction, cobalt, iron, and ruthenium was well known as good active. Ruthenium is too expensive, so research is being focused on cobalt-based catalyst or iron-based catalyst. The iron-based catalyst has good performance to produce hydrocarbon, but it also generates carbon monoxide as a byproduct and requires a process temperature of over than 300 degrees. And cobalt-based catalyst is active at low temperature of 250 degrees and produce very low carbon monoxide. However, it produces high methane production. Therefore, I am researching to overcome the disadvantage of cobalt-based catalyst. Here is my research. I promoted some methods to enhance the carbon chain growth activity, and the characterization is conducted as follows. There are three elements for catalyst: active, promoter, and supporter. In general, manganese, sodium, aluminum, zinc, and potassium was selected for promoter in this reaction. In my research, I select manganese and zinc as promoter. And I synthesized Mesoprose structure catalyst by using Kit 6 hot template for supporter to increase the active site of the catalyst and reduce deposition by wax. And I confirmed the structure by entudoption and TEM images. And by entudoption analysis, I confirmed also surface area, pore volume, and pore size of these catalysts. In addition, EDS confirms that each metals were well dispersed and the metal phase was confirmed by XRD analysis. The synthesized catalyst exists in the form of oxide phase. This oxide phase is not active in these reactions, so it needs to be changed to a metallic phase by reduction process. So I analysis using H2TPR to find the appropriate reduction temperature. The following is the result of the catalyst activity test in fixed bed reactor. After the reduction at 400 degrees for 12 hours with H2, the CO2 hydrogenation reaction was carried out at 250 degrees for about 40 hours at 40 bar. The result shows CO2 conversion and CO selectivity and hydrocarbon selectivity as distributions as follows. I prepared Mesoprose structure cobalt mangan catalyst and Mesoprose cobalt mangan aluminum catalyst and cobalt manganese zinc catalyst with the same molar ratio of manganese. From this compare, I confirm the effect of each promoter. And I changed zinc command to confirm the performance according to the amount of the promoter metals. And also from this time of stream figure, it can be known that catalysts are stable for a long time. This is end of my presentation. Thank you for listening.